Today we're going to go over or start a new topic, and we are going to first start by talking about sequences and series. So what is a sequence? Well, an infinite sequence is a function whose domain is a set of positive integers. Okay, so it's a function. The domain is a set of positive integers, so starting with 1, 2, 3, 4, and so on. The function values a1, a2, a3, a4, these are all values of the function, are the terms of the sequence. If the domain of the function consists of the first n positive integers only, then the sequence is what we call a finite sequence. We're talking about this as a function, which means that the domain is a set of all positive integers. So really what you're saying is you can come up with the first term, second term, third term, as long as it's a positive integer. You won't be able to come up with the 2.5 term and so on. So it has to be positive integers. We're not going to have the negative fourth term, right? Okay, so that's the domain aspect there. And then the function values, so you have some rule that gives you what the next term will be. So if you're trying to find the 7th term, there will be a function for you to figure out what the 7th term is. And so whatever the 7th term comes out to be, those are the function values, right? That would give you a7, for example. All right, so next, let's look at an example where we actually are given a function and we need to find the first 4 terms in the sequence. So here you're given a sub n equal to 3n minus 2. If you're finding the first 4 terms, we need to plug in n equals 1 all the way up through n equals 4. So let's start with n equals 1. So a sub 1 is equal to 3 times 1 minus 2, so 3 minus 2, which is equal to 1. So that means the first term is 1. Plug in 2 for n. We have 3 times 2 minus 2, which is equal to 4. A sub 3, 3 times 3 minus 2, that's 7. A sub 4, 3 times 4 minus 2, that's equal to 10. And we only need the first 4 terms, so we're all done here. So our first 4 terms are 1, 4, 7, and 10. And you can also see the pattern that's coming out of this, and this is what we call, as we'll learn later on, you can see that we're just adding 3 in order to get to the next term. But there are advantages to having a function. For example, if you're trying to find the 100th term, you don't want to have to do this so many times in order to get the 100th term. And so having the function notation here will help us with that. Let's take a look at the next example. Find the first 4 terms of the sequence given by this function here, a sub n equals 3 plus negative 1 to the nth power. So we'll do the same thing as in the last example. In this case, n is in the exponent. So we have a1 is equal to 3 plus negative 1 to the first, which is equal to 2. A sub 2, now we have negative 1 being squared, so that ends up being positive, so that's 3 plus 1 equals 4. A sub 3, this is going to look like the first term, because now we're raising it to an odd power. That's going to come out to 2. And then a sub 4, we're raising it to an even power, so this will look like the second term. So we have 3 plus positive 1 is equal to 4. And you can kind of guess what's going to happen next based on what you're seeing with the pattern, with whether it's an even or an odd integer and what that does to the function. All right, now what if we had to come up with the expression? So in example 2, we have 1, 3, 5, and 7 given to us, and it says to write an expression for the apparent nth term, so a sub n, of the sequence 1, 3, 5, 7. So what I like to do is I like to write out which number term it is. So the first term is 1, the second term is 3, third term is 5, and the fourth term is 7. Because we're writing an expression in terms of n, it's helpful to have n to work with and try to figure out what do we have to do to n in order to get a sub n, which is the actual term itself. So this takes a little bit of practice and looking at the numbers and playing around with them a little bit. But here in this particular case, you can see that each term is 1 less than 2 times n. So if you look at your values of n, if you multiply each of those by 2 and then subtract 1, you end up with that term, right? So 1 times 2 minus 1 gives you 1. 2 times 2 is 4, minus 1 gives you 3. 3 times 2 minus 1 gives you 5, and so on. So that's the pattern here. So we're going to write that down in algebraic terms. So that's going to be a sub n equals 2 times n minus 1, right? 1 less than twice n. All right, let's try another example like this. So we have 2, 5, 10, and 17. And again, these are the first 4 terms in this sequence. So again, I would write this down in terms of n. So n is 1, that gives you term. The term is 2. When n is 2, we have 5. When n is 3, we have 10. When n is 4, we have 17. So again, it takes a little bit of practice to work with those numbers and see if you can find a pattern. In this particular case, if you take a look at your values of n, if you were to square each of those, it gets you pretty close to the actual term, right? So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. They're each off just by 1. So you'll notice that the pattern here is that each term is 1 more than the square of n. So writing that in algebraic notation, that would be a sub n is equal to n squared plus 1. All right, next we have recursive sequences. So recursive sequences, this is where you have a sequence where all terms of the sequence are defined using previous terms. So a very classic example of this is the Fibonacci sequence. So if you've heard of the Fibonacci sequence, but don't know what it is, this is how we define it. So we would say A0, so we actually start with 0 here, is equal to 1, and A1 is equal to 1. So the first 2 terms you have are both 1. Now, the formula, the rule that we use for the Fibonacci sequence says, in order to get a sub n, you take a sub n minus 2, add it to a sub n minus 1. What does that mean? That means you add the previous 2 terms together to get the nth term. Okay, so if we were to apply this, if we were trying to find a sub 2, then we would need to do a sub 2 minus 2, which is a0, plus a sub 2 minus 1, which is a1. So we are given a0, we're given a1, so this is 1 plus 1, which is 2. Right, to get a3, we have to do a1 plus a2, right? So it's 2 terms before it plus the 1 term before it. So that's 1 plus 2, which is 3. Do the same thing for a4. That would have to be a2 plus a3. So 2 plus 3, which is equal to 5. And then for a5, we have to do a3 plus a4, and that gives you 8. And so you can see the pattern here, exactly as it's stated, is you take 2 terms before it, add them together to get the next term. So writing it out as a sequence, we have 1, 1, 2, 3, 5, 8, and you can probably see this at this point and say, without having to write all the notation, what the next term is going to be. It'll be 13, and then 8 plus 13, which is 21, and so on. All right, the next thing we're going to talk about is summation. So when we talk about summation, this is very much related to sequences of numbers because now you are summing the sequence of numbers. Now, we'll talk a little bit more in depth in just a little bit about how you can have a finite sequence versus an infinite sequence and summing those. How do you go about summing those? But before we get into that, we're going to talk a little bit about notation. So summation notation, which is also known as sigma notation, represents the sum of the first n terms in the sequence. So here's the summation notation. It's called sigma notation because the thing that looks like a capital letter E is the letter sigma, hence sigma notation. And you'll notice that next to it, we have a sub I. And then this says that this is equal to the sum of a1 plus a2 plus a3 all the way up to a sub n. Now, how do we know that it goes from A1 all the way up to AN? So if you look at the sigma, at the bottom, we have what we call the index. That letter I is the index. And then whatever that's set equal to on the bottom, that's the lower limit. So in this particular case, I is equal to 1, so the lower limit is 1. Above the sigma, we have, it'll either be a letter like we have here. It will probably be a number if you're actually asked to sum up the first however many terms. In this particular case, this goes up to n. So n is what we call the upper limit. So again, we had to define, when we talk about sequences, that the domain is always going to be positive integers. So you're always going to go up. So from A1 to A2 to A3, all the way up to A sub n. Okay, so just an example, mostly for us to make sure we understand this notation. We have the sigma notation here. We see the index down below is I, and the lower limit is 1, and the upper limit is 5. So we're summing 5 terms, right? Terms 1, 2, 3, 4, and 5. And in order to figure out what those terms are, we have to use the rule that's given to us here. So 3i is the rule. So to get the first term, we would do 3 times 1. That gives us the first term. To get the second term, we would have to do 3 times 2, and so on until we get up to the 5th term. So 3 times 3, 3 times 4, 3 times 5. And we have to add all of those terms together. So this is really 3 plus 6 plus 9 plus 12 plus 15. Add those together, and that gives us 45. All right, let's do one more example to make sure we are comfortable with the sigma notation. All right, this particular case, you'll notice it does not start at 1. It says k equals 3 is the lower limit, and the upper limit is 6. Use the rule there, 1 plus k squared, to find the third term, the fourth term, the fifth term, and the sixth term, and then we'll add them all together. So we have 1 plus 3 squared, that gives us the third term. 1 plus 4 squared, that's the fourth term. 1 plus 5 squared, and 1 plus 6 squared, and then we're going to add all of those together. So this is 10 plus 17 plus 26 plus 37, which is equal to 90. All right, a couple properties of sums that I would like to go over. The first one here, it says that the sum of the first n terms of C times A sub I is the same as if you were to find the sum of the first n terms with A sub I and then multiply that whole thing by C. So C is any constant. So if there is a constant, you can always pull it out, find the sum of all the terms in terms of A sub I, and then after you find that sum, then multiply by C. This can be helpful if, for example, the numbers get really large. It can make it easier in order to find that sum. It might be less work because you don't have to multiply each term by C. You just have to sum up all those terms and multiply that one term by C. All right, the second property of sums, in this particular case, you can, the sum of, if you look at what's in the rule here, A sub I plus B sub I, you can actually, as long as you are separating it into the sum of the first n integers for both, you can separate it into 2 separate sums. So you could sum up the first A sub I terms from 1 all the way to n, and then sum up all the terms for B sub I from 1 all the way up to n, get the answer for both of those, and then add them together, and that would be the same as if you were finding the sum of A sub I plus B sub I. And the same thing applies for the third rule, or the third property, which is the same thing happens if you are subtracting those two. So A sub I minus B sub I can be split into 2 separate summations After you find each of those summations, then subtract. Okay, the next thing we're going to talk about are series. So when we talk about series, a finite series, oftentimes you'll also see it called an nth partial sum. So you might see a fourth partial sum, means the sum of the first 4 terms. Okay, so a finite series is the sum of the terms of a finite sequence. Okay, so for example, you're summing up a sub 1 all the way up to a sub n. Right, this is what we've been doing so far. And then the second type, an infinite series, is the sum of the terms of an infinite sequence. So in this particular case, if you look at the notation, we have the upper limit being infinity, right? So it's not some number n, right? It goes to infinity. So notice that the way I've written it here, I've written it as a sub 1 plus a sub 2 all the way up to a sub I, but then it doesn't stop there, it continues plus dot dot dot. So it continues. Now you might be thinking, well, isn't any infinite series just going to equal infinity? That's not necessarily the case. We will look at an example where that isn't the case, and you can see how we can actually find a sum of an infinite sequence that's equal to very much a value that you know, and it's not just it equals infinity. All right, so let's take a look at this example. So here we are asked to find the sum of the values from 1 to infinity with the rule 3 over 10 to the I power. So for part A, it says to find the third partial sum. And for part B, you're just finding the sum. So you're finding the sum of the infinite sequence. Okay, let's start with part A. So the third partial sum means sum up the first 3 terms in the sequence. So really all we need to do is put our upper limit to 3 and do what we were doing in the last couple of examples. So 3 over 10 to the first plus 3 over 10 squared plus 3 over 10 cubed. This one might actually be pretty helpful to write it in decimal form. In decimal form, this would be 0.3 plus 0.03 plus 0.003. So this is equal to 0.333, and it stops there. All right, so that's our answer for part A. For part B, now you might be starting to see how we can actually come up with a value for something that is an infinite sequence. So in this particular case, we know we're going to start off with those first 3 terms exactly the same, but then we would continue. So we would continue to add 3 over 10 to the 4th, 3 over 10 to the 5th, 3 over 10 to the 6th, and so on to infinity. Now, if we were to do that, we'd end up with what? 0.3 plus 0.03 plus 0.003 plus 0.0003 plus, and you would just continue to add an extra 0 after the decimal place before you get to the 3. Well, what happens when you add all of those together? You don't actually need to know what all those values are. You can hopefully start to see the pattern here. If you were to continue, that would mean that you would continue to have another 3 in the next place, right? Which means if you were to sum them all together, you'd end up with what? 0.3 repeating, and 0.3 repeating, as you know, can be expressed as a fraction, right? As 1/3. So the sum of this particular sequence, this infinite sequence, is going to be equal to 1/3.